we will now have an initial graph, which when evolved by mean curvature flow oscillates indefinitely, even though it oscillates more and more slowly, and when evolved under heat flow will stabilize. Let's first talk about a solution that oscillates indefinitely for the heat flow, and this is a one-dimensional argument. Let In be n factorial plus 1 and n plus 1 factorial minus 1. So the plus 1 and minus 1 outside of the factorial are just there so that there is some room to transition and make this graph smooth. U0 is going to be 1 if x is in I2k plus 1 and 0 if x is in I2k. So it looks like the graph in dotted, except I didn't make room for the plus 1 or minus 1. So you can draw that and recall U0 is a C2 alpha Herder continuous function. So you can make it C2 alpha by using smooth transition between 0 and 1. Now we have that lim inf of v of 0t equals 0 and lim sup of v of 0t equals 1. So at the origin, if you take average over larger and larger ball, it's not gonna converge to a limit because it's gonna be 0 for y and then 1 for quite a long while. So the average then goes up to 1. Then it's going to go back to 0 for a very, very long space. So the average goes back to 0. Then it's going to go up to 1. And somebody told me this is the example of placing a teacup, a hot tea in a cup, into a cold fridge, into a hot house that's sitting in the middle of a blizzard. So the temperature of the tea is gonna go down to 0, and the fridge is not plugged in. So then the fridge will take the temperature of the house, will go back up to 1, and then the house, which is not heated either, so heat flow, we just turn off all the power and see how the temperature changes. So then again, the house sitting in the middle of a blizzard, the temperature will go down, which makes the temperature of the tea go back down to 0. So it oscillates indefinitely at the temperature at the origin goes up and down more and more slowly, but the lim inf is 0 and the lim sup is 1. So that's a solution that oscillates. Now, I drew black lines so that this is the solution U0 that is smooth. For our initial data, we're gonna put spikes. So this is the orange U0 is not the U0 we will take. We just put spikes where it's 0. And it's gonna look like that. So the red part is where it's 1, and where your solution was 0, or your initial data was 0, you put spike at, again, integer nexuses. This is now a 2D graph, so wherever it's 1 or changing between 1 and 0 in the transition region, you just cross it by R, and wherever it's 0 on the bottom, we put spikes. Now, what happens to this graph? Again, we can see that the heat flow, for the heat flow, we have uniform convergence to 1. The same idea, if you take larger and larger balls centered at any point, the averages will go to 1 because we made sure of that. So the solution to the heat flow will stabilize at the constant 1. Now, what happened to the mean curvature flow? Let's see. For the mean curvature flow, I do the same thing. I put donuts, which are sort of the lighter blue donuts around each spike. And if you evolve that, again, at extinction time t star, the spike would have to come down through the hole and be at most height delta naught. The look like oval, oblong, darker blue are donuts. Instead of being like this, they're turned on their side, so you only see the side. And I put them there to show that close to the transition, the graph doesn't go up too fast. So the donut extinction is still gonna be t star. And if you remember the width, or the width this way, how wide it is, was less than 1/2. So if you put it this way, then the graph can go up past 1/2 before extinction time. So the mean curvature flow, we use them as barrier. U at t star is less or equal than R0 on the odd slab. That's just the second argument I gave you with the donuts that were vertical. So the height here was R0, and it can't get past R0, at least not before t star. And it's going to be 1 plus R0 on the even slab. So on the even slab, when the graph was 1, you put, again, donuts on top. And so the slab can't get past these donuts before time t0, before extinction time of the donuts, because the donuts sort of stay here and shrink. What do we have? We have U at t star being at less than R0 and being less than 1 plus R0 on the even slab. So this is a profile picture of the initial graph. Remember the spike? The transition region we took is about 1/4, and well, there's kind of, well, not really a typo. The initial graph W0 is in R2, and psi0 is our oscillating function in R1. Okay. So mean curvature flow, the solution oscillate. So psi of t is going to be a lower barrier. Remember, your initial graph W0, if you put spikes on the bottom, it's going to be greater or equal than psi0, well, cross R. So if I evolve psi0 by mean curvature flow, it will stay below the evolution of W0 under mean curvature flow. So psi of t is a lower barrier for the solution U at t. That means that the limb sup of U of 0t is greater or equal than 1, because the limb sup of psi was greater or equal than 1 at the origin. Now psi0 plus R0 is an upper barrier, but only after time t star. Remember, in the previous slide I showed you that it's at most R0 on top, 1 plus R0 on top, and it's at most R0 on the bottom. So if I add R0 to my psi of t. So if I evolve psi and use R0, I have an upper barrier after time t star. So the limit inf of u of 0t is less or equal than R0. And R0 can be taken arbitrarily small, so it can be less or equal than any epsilon. That means that the mean curvature flow will oscillate between 1 and epsilon, and 1 and epsilon, 1 and epsilon. As the example of the temperature of the T, it oscillates more and more and more slowly. And if you recall, there is Ecker-Husken showed in their paper about entire graph that in the limit, if you have an entire graph that's Lipschitz with good conditions at infinity, which this satisfies, then it will converge to a solution that is self-similar. And here I showed to you that it's oscillated, so there's seemingly no convergence. You have to remember that the Ecker-Husken result is along a subsequence. So this result does not contradict it. It still will, there is convergence to the flat plane along a subsequence. But if you take the whole sequence, the solution oscillates. And that's the conclusion of my talk. Thank you for following it. And if you have any question, you can email me, or you can ask them at the question and answers.